Hey guys, today we're going to start Chapter 5. We're going to start in Section 5.2. Chapter 5 eventually is going to talk about exponential functions and logarithm functions, which are things that you saw in Algebra 2. Those two functions are inverses of each other. They undo each other, kind of like adding and subtracting and multiplying and dividing are inverses of each other. So before we get into that, the first thing we're going to do is we're going to talk about inverses. But before we can talk about inverses, the very first thing we're going to talk about are what are called one-to-one functions. So we've talked about functions before. A one-to-one function is a function where every x has one and only one unique y that it matches up with. So, like, this is an example of a function. Okay, it's okay that these two x's happen to have the same y value. 2 squared is 4, but also negative 2 squared is 4. That's okay. That's a function. But it's not a one-to-one function. So a one-to-one function is something like 2 times 3 will give you 6. And 3 times 3 will give you 9. You're never going to get that 6 again if you're just multiplying. So that would be an example of a one-to-one function. And that's what we're going to be talking about mainly today. Okay, so that's a one-to-one function. That's a function, it's just not one-to-one. This isn't even a function, okay? If one x gets split to two different y's, that's not a function. One way to tell that you have a one-to-one function, if you're looking at a graph, not only does it have to pass a vertical line test, but it would have to pass what's called a horizontal line test. So if you draw a horizontal line and cross the graph twice, that's not a one-to-one function, okay? These two x's have the same y value, so that's not going to be a one-to-one function. Okay? Now, if you're looking, so down here I've got some maps, I've got ordered pairs, I've got some graphs over here. So a mapping is pretty easy. Everything here, so determine whether the following functions are one-to-one. Well, each state over here has one and only one unique population, and there's no states that have the exact same population, so yes, this would be a one-to-one function. Over here has to do with animals and their life expectancy. Well, dog and cats both have a typical life expectancy of about 11 years, so this is not a one-to-one function. Okay, it's a function, it's just not one-to-one, so no. For C, okay, that's a graph. If I draw a horizontal line, everywhere I draw a horizontal line, I'm going to cross that once and only once. Okay, so yes, that would be one-to-one. E, this example would not be. I know there's D over here, but might as well do this one. So this is no. Okay, if I draw a horizontal line, I'm going to hit this a whole bunch of times. Okay, for a set of ordered pairs, well, when we were looking for functions, we were making sure that the x's didn't repeat. Make sure there wasn't like a 1 that got matched up with a 3 and then a 1 that got matched up with something else later. Well, for a one-to-one function, you're also going to make sure the y's don't repeat. So the x's, I have a 1, a 2, a 3, and a 4, so it's a function. But then for the y's, I have a 5, an 8, an 11, and a 14. So there's no repeating. So yes, this is a one-to-one function. Okay? Now, the reason we talk about one-to-one functions is if you have a one-to-one function, then you have what is called an inverse. You can have what's called an inverse function, okay? And an inverse function is a function that will undo the original function. So if you look at this little composition that I have right here, this little two function machines, if I put a 10 into this function, 8 times 10 plus 5, I get 85 as an answer. Well, if I put an 85 into this function, where you take 85 minus 5 and divide it by 8, you'll get 10 as an answer. So this function exactly undid what this function did. Okay, this function takes your input, multiplies it by 8, and adds 5 to it. This function subtracts 5 and then divides by 8. So it does the exact opposite, and it gets you right back to where you started with. This is the inverse of that. Okay, that's an inverse function. Again, they just undo each other. This is the symbol we use. It's f with a little -1 exponent right there. It just means the inverse function. So if f of x is 8x plus 5, then the inverse of f would be x minus 5 divided by 8. Okay, that's inverse. Notice that when I did this, this is my domain. Okay, so that's my input value. I put it into this function and I got this range value, okay, of 85. But then that 85 was the domain going into this inverse function, and then it spit out this range value of 10. Okay, and that's a property that's true with inverses. The domain of a function is the range of the inverse. Okay, so here's a function. These are a bunch of x values, a bunch of domain values, and when you plug them in, you get a bunch of y values, a bunch of range values. But your inverse goes the opposite direction. So your inverse, all these numbers over here that were the range of f, that's what you're going to be putting into your inverse function. So that's the domain of the inverse. And then the answers you're going to get, which were the original inputs, these are now your outputs. You're going to be getting these answers. So this is the range of the inverse. So the idea is they just switch. That's all you have to remember, that they switch. Okay, down here, I've got an example. This is a one-to-one function. I've got 3 students over here, and I've got the cars they drive. Find the inverse of the following functions. State the domain and the range. Well, the student over here, this is the domain, and the car they drive, that's the range of this little function we have. So the inverse would be, I tell you the car, so I say there's a Saturn with its lights on in the parking lot, and you say, oh, well, that's Dan's car, so I need to go tell Dan to go turn his lights off. Okay, so it goes the opposite direction. So if there were multiple students that had a Saturn, this wouldn't be a one-to-one function, and I couldn't do that. I couldn't say, hey, there's a Saturn, and we'd say, well, we have no idea who that is. There's a bunch of kids that drive a Saturn. But in this case, this is a one-to-one function, so we can do that. So this is the student over here. Okay, so the Saturn, the Pontiac, and the Honda are the domain of this problem, and then the student, Dan, John, and Michelle, are the range of the inverse. Okay, so they just switch places. For a set of ordered pairs, okay, obviously the x's, these are your domain values, and the y's, those are your range. But the inverse of this function would literally be just take each ordered pair and flip it. So 8, 2, 11, 3, and 14, 4. And that's the inverse. So for this one, the domain is now the 5, the 8, the 11, and the 14. And the range would be the 1, the 2, the 3, and the 4, which was the domain of the previous example. Okay? So that's it. Inverses, you just flip them. Now, if you look on the last page, graphically, what happens is all your x's and y's flip-flop. So if I've got, here's my original function. If I've got the point AB, so this is like over, let's say this is over 1 up 4. Okay, then my inverse is going to have over 4 up 1. All the x's and y's just trade places. Okay, so a function and its inverse are symmetric, but they're symmetric in a weird way. They're symmetric across this line right here. This is the line y equals x. So that's just, like, it has all the points 1, 1, 2, 2, 3, 3, all the points where x and y are the same. Well, since your x's and y's are flipping, then it flips across this line right here. And that's what this line of symmetry is showing us. Okay, so this line, these two functions, this is f of x, this is this is the inverse of f of x. Okay, they're symmetric across this line. But again, the key is just switch your x and your y. So if I give you a graph, so this little, I know it's not a very exciting graph over here. This has the point -1, 0. It has the point 0, 3. And then it has the point 1, 4. If I asked you to draw the inverse, you would just take each of those points and you'd flip them. So you need to graph 0, -1, which would be down here. You need to graph 3, 0, 1, 2, 3, 0, which is right here. and you'd have to graph 4, 1, which would be 1, 2, 3. We'll approximate 4 out here, and then we'll go up 1. Okay, and so we would get this little picture, which again, if we drew this little imaginary line, y equals x, it's symmetric across that. Okay, these points just get flipped over to here. Okay, so for a graph, that's what you do. Now, what if I give you a function? So this is where this is all trying to get to. If I give you a function and I want to figure out what is the inverse of this function. Okay, so here's what we're going to do. First thing you're going to do is you're going to rewrite this function with a y. So instead of function notation, let's turn it into y. So y equals -1/3 x plus 1. Okay, it's a little bit easier to deal with. Now, the inverse switches your x's and y's. So that's what we're going to do. We're going to take the x and the y and we're just going to flip them. So we're going to put the x over here and we're going to put the y over here. Now, technically, we're done, but we're not. Okay, this is the inverse. We have created the inverse. But now we need to resolve it for y, so we can write it using function notation, and then we'll be done. Okay, so right now, we're not quite there yet. So we need to get the y all by itself. So we need to move the plus 1 to the other side, so that's x minus 1. Now we need to get rid of this -1/3 that's multiplying our y. The easiest way to get rid of a negative is to multiply by a negative. And the easiest way to get rid of a fraction is to multiply by its reciprocal. So if I multiply both sides of this equation by, so think of this, -3. Okay, the negatives will cancel, these two 3's will cancel, and I'll just have the y by itself. But I'll have to do that on this side as well. Okay, you could leave it like this. You could distribute. That'd probably be the better way to do it. So -3x plus 3 equals y. Which is our inverse function. Okay, so use the inverse function notation. A lot of times when we make this little switch, we use y and we put a little prime to remind ourselves that we've made this switch. This is not the original y. We took the x and y and switched it, and we get this little y prime. You may see me do that, you may not, but this is the important part, that you stop at the end and you write this. Okay, now, last thing, if you look up here, the directions say find the inverse. Okay, we did. This is the inverse. And state the domain and range of each. Now, we know how to find the domain of a function. Okay, we can look at this function and I can tell you the domain is all real numbers because there's no x in a denominator and there's no radicals or anything. So that's all real numbers. I can look at this function and I can tell you the domain of that is all real numbers. That's all I need to know how to do. Because if I know each of these domains, then I can also use the fact that the domain of this function is the range of this. So if that's all real numbers, this is all real numbers. Range. And the domain of the inverse is the range of this. So all we're really going to do is find the domain of each, and then we're just going to take the information and we're going to flip it. Okay? So that's that one. All right, so second example. So again, first things first, we're going to rewrite this as y equals 3x cubed plus 2. We're going to switch our x and our y, so x equals 3 y cubed plus 2. Okay, and now our job is to resolve this for y. Okay, so we need to get rid of the plus 2, so x minus 2. Now we need to get rid of the 3 that's multiplying, so we're going to divide by 3. And now our y is being cubed, so we need to take the cube root of both sides. So that'll be our final answer over here is the cube root of x minus 2 over 3 equals, and then again, we want to rewrite this using the inverse notation. So this is the inverse function of our original function. Again, domain and range. All we're really going to do is we're going to find the domain of each of these. Okay, so this is a cube. There's no fractions, no radicals, so the domain is all real numbers. And we're going to jump down here and find the domain of this. Now, there is a fraction, but there's no x in the fraction, so that's not an issue. There is a radical, but this is a cube root. And cubes, you can take cube roots of positives, negatives, anything. So there's no restrictions with a cube root. So again, our domain is all real numbers. And if each of these domains are all real numbers, then when you flip them, this range will be all real numbers, and this range will be all real numbers. Okay? All right, last one. This is the only one that's a little tricky, so make sure you're paying attention. All right, first things first. We're going to rewrite this as y equals, and then I've got this function on the other side. And now we're supposed to switch all the x's and y's. Well, this one has two x's. So when we switch it, it's going to have two y's. So we're going to have an x equals, and then it'll be 2y over y minus 1. Now, whenever you have multiple variables, so we're trying to solve for y, but we've got more than one y. There isn't just one y to solve for. So we're going to have to, the first thing, whenever you got a y in a denominator, you want to get rid of that. Okay, you can't solve for something that's in the denominator. So the first thing I would do is I would cross multiply. Okay, now if I multiply, I would get xy minus x equals 2y. Okay, so now I don't have fractions anymore, so that's helpful. Okay, next, if I have two y's and I'm trying to solve for y, I need to get those y's together. So I'm going to get the y's on the same side, and then anything that doesn't have a y, I'm going to leave it on the other side. So I've got a y over here. I'm going to take this xy, this whole term, xy, and I'm going to bring it over to the other side. Well, this is a positive xy, so I'm going to get rid of it by subtracting it. This x is going to be negative x equals, and then 2y minus xy. And the reason you get the y's together is because now both of these terms have a common y that you can factor out. So negative x equals, factor out the y. It's the greatest common factor. It's going to leave you with 2 minus x. And now our 1y is multiplying by this expression, this binomial. So we can divide by that whole thing, negative x divided by 2 minus x equals y, which is our inverse function. Okay, so this function is the inverse of that. Now, I will tell you, there is a different way to solve this. If I would have moved my y's to the left instead of moving them to the right like I did, it'll make this fraction look different. It'll be equivalent, but it'll just look different. Like all the signs will be changed. Like this will be a positive x, this will be a negative 2, and that'll be a positive x. Exact same function, it's just depending on which way you solve it. Okay, so not a big deal. Again, this is our answer. This is our inverse function. But we're also supposed to find the domain and the range. Well, these do have some domain restrictions. Okay, the domain of this is x cannot equal 1. So x cannot equal 1. And the domain of this would be x cannot equal 2. But these domains are the range of the other ones. So if this has a domain that x cannot equal 1, that means this has a range that y will never equal 1. There is no way to get a 1 with this one, with your y value. Okay, that's like it's a horizontal asymptote. You'll never get a 1. Okay. If the domain of my inverse is x cannot equal 2, that means the range on this is y will never equal 2. Well, again, if you look at this, x over x, 2 over 1, that's a horizontal asymptote. And this is one of those horizontal asymptotes that you don't cross. So that has a range restriction. And that's it. Okay? So take a look at the homework and let me know if you have any questions. Thanks, guys.